This video lecture is going to focus on Lewis dot diagrams that show covalent bonds. So when you think about Lewis dot diagrams, they're a way of showing the shared pairs of electrons in a covalent bond between nonmetals. They're a way of modeling it to show what electrons are in bonds and which electrons are lone pairs on the outside. For example, here we have hydrogen with one shared pair of electrons. A line equals a shared pair. These dots around the chlorine represent unshared pairs. They still need to be on chlorine because we're trying to obtain the octet, or in hydrogen's case, the duet. So how do we draw these and how do we represent these covalently bonded molecules? First of all, we're going to take the example of PCl3. You want to find the total number of valence electrons by looking at the family number. Phosphorus is in 5A, so it has 5 valence electrons, and there is 1 phosphorus. Chlorine has 7 valence because it's in group 7A, and there's 3 of them for 21. Added together, we have 26 total valence electrons. You cannot exceed this number. You cannot go under this number to have a valid structure. If you get a polyatomic ion that is negatively charged, you have to add electrons for each negative charge. If it is a positively charged polyatomic ion, then you must take away 1 electron from the count. Ammonium NH4 1+ is a good example of it. It has a total of 8 electrons in its count, not 9, because it has a positive 1 charge. Next, we make a skeleton structure, meaning we're going to link things together to get a starting point. Central atom is always the least electronegative. Hydrogen is always surrounding. Halogens are usually surrounding. Carbon, that's a likely suspect to be a middle type of atom. When we link them all together, we're going to put single bonds around the phosphorus. Notice that each line represents 2 electrons. 2 electrons here, 2 electrons here, 2 electrons here. We just used up 6 of our total. Notice we're keeping a running track down here at the bottom. 26 minus 6, we have 20 left. Once you make single bonds, now fill the octets of the outer atoms. Always start outside in. So notice we got 6 dots on that chlorine, 6 dots on that chlorine, 6 dots on that chlorine. So we subtracted 6, subtract 6 more. Now we're down to only 2 electrons total out of our count of the original 26. Next step, fill the central atom if any electrons you have left. So we have 2 left. Phosphorus was short 2 for an octet, so we put that as a lone pair on top of phosphorus. Check the octets, 2, 4, 6, 8 on chlorine, 2, 4, 6, 8 on chlorine, 2, 4, 6, 8 on chlorine, 2, 4, 6, 8 on phosphorus. Lewis diagram, all 26 electrons on the structure. If you run out of electrons before you get an octet, you may have to do multiple bonds. Notice in this HCN structure, carbon doesn't have an octet yet, even though we have all the electrons on the structure, which is 10. So now you can take any electrons that are on the nitrogen that are unshared pairs and move them into multiple bonds. Since carbon was 4 short, we took the 4 electrons from the nitrogen, moved them inside to make a triple bond between the carbon and nitrogen. You can take those electrons from any unshared pair and move them in to satisfy the octets. Formal charges is something that's a lot different. We don't really talk about this in Chemistry 1 or Intro, but this is how to figure out if one Lewis structure is better than the other. And these are the rules for it. For each atom, count the electrons in lone pairs and half the electrons it shares with others. Subtract that from the valence. So if you look at oxygen, oxygen has 6 total valence electrons from its group number. Now, where do we come up with this electrons assigned? It has 2, 3, 4 here, and it has 4 in the middle being shared. Well, we take those 4 electrons shared and cut them in 2. So there's only 6 being assigned. Subtracting it gives you a formal charge of 0. Carbon has 8 electrons being shared, but we can only take half of them for 4. It has 4 from the table. So this top row is all from the periodic table. This is from taking the unshared pairs and half the shared pairs and subtracting them. Same thing for oxygen here. 1, 2, 3, 4. Half of the 4 that are shared is 2 more. 6 electrons assigned to the atom. 6 comes from the periodic table. Here's another valid Lewis diagram for carbon dioxide. Notice here the formal charge. You have 2, 3, 4, 5, 6, 7 assigned to the oxygen here. It has 6 off the table. It has a formal charge of -1. Carbon has 8 shared, so it's 4 and 4, no different. This oxygen is different. It has 2 that are unshared, and then it has 6 shared. Half of that, or excuse me, 2, 4, 6, half of those being shared, that gives you 3, plus 2 gives you 5. So when you think about how this looks, this value here is all from the periodic table. So you look at the group number, and that goes right there on that row. This bottom row, you have to take the unshared pairs, count as 1, whatever the number is of unshared pairs. So you got, for example, here you had 2, 3, 4, those all count, and then it's half of the shared pairs. So what the heck does that mean in terms of valid Lewis diagrams following that formula? The best Lewis structure is the one with the fewest charges. So if you can get them all to be 0, that's awesome. If they don't all equal 0, put a negative charge on the most electronegative element. So take a look at these that we've got here on the screen. -2, 0, +1. -1, 0, 0. 0, 0, -1. Now oxygen is more electronegative because it's farther to the right of the periodic table. So thinking about the best Lewis structure for this, oxygen gets a -1 for its formal charge. 3 would be the most valid Lewis diagram. When we think about Lewis diagrams, we can also see where double bonds can be in multiple spots, and this is called resonance. This is a valid structure for ozone. That double bond is on the left, could just as well be on the right. It's not really true that it looks exactly bent here with these O and O bonds being the same length. They both have a formal charge of -1/2. So how do we figure out what it looks like? Well, in fact, in nature, this double bond goes back and forth and vibrates like a drum resonates, or it vibrates and shakes to both sides. This is what the molecule truly does. It bounces back and forth in nature between both sides of the oxygen bonds. If you look at the space-filling model, think about it like paint. Blue and yellow make green, just as these two resonance structures make this electron space-filling model seem where the electrons are at. Notice that most of the electrons are still found at the bottom, and here at the top we have fewer electrons right in the middle. So these two resonance structures equal the one true structure of ozone. Now, when you think about electrons and resonance here, resonance structures, they delocalize the electrons, meaning that they can bounce between all sorts of 3 different locations, or at least 2 different locations, like in this example. The electrons can be here or here, and that shows the 2 resonance. Notice we're depicting with an arrow to show that it goes back and forth like a vibrating drum. They're not localized or locked into place. They can bounce back and forth. That's what resonance really is. They don't always sit in one spot. This is a compound called benzene, and it's got 2 resonance structures. And if you look at it, it makes a hexagon shape, and it shows where the double bonds can rotate. The double bonds can be on the top or on one side of the hexagon. See how the 3 lines alternate 2 different ways? This is really delocalized because in this ring structure, the electrons can move in many different locations. This is a great example of resonance within this ring. There are some exceptions to the octet rule. Ions or molecules have odd numbers of electrons. You can have less than an octet for some, and some that can have more, an expanded octet. It's not very stable to have an odd number of electrons, but you could have them. Like, for example, here you've got an odd number of electrons dealing with oxygen and nitrogen. If you get an odd number of electrons in a structure, what usually happens between the 2 of them, they're really super reactive, and they want to react quickly to get that stable set of valence. Some have fewer than 8. Boron, the prime example of this, it only has 3 valence electrons. It's a metal, but it's found in the p block. It doesn't have a strong ionic character, so it's likely to share with somebody, especially if it's really electronegative like fluorine. So notice, if we look at filling an octet for boron, if we did that, we would give it a negative charge. The central atom never gets a negative charge. So this is not a real accurate depiction of boron. You don't want the negative element to be on the central atom. You want the most electronegative element to be negative. Notice here fluorine doesn't get a negative formal charge on any of these. So this cannot be a true valid Lewis diagram of boron trifluoride. In fact, because boron only has 3 electrons to share, the dominant structure is found on this side. This would give a formal charge of -1 to the fluorines, and boron would be happy with 6 valence electrons. That's the more dominant Lewis diagram. The lesson here is filling the octet of the central atom gives a negative charge in the central atom. It doesn't happen. If that happens and you get a negative on the central atom, it's more likely to be less than the octet, like we have on the left-hand side. Some atoms can have an expanded octet. You have to be in the 3rd energy low or below. If you remember with your quantum numbers, there's no such thing as a 2d orbital, but there is such a thing as a 3d orbital. Phosphorus sometimes can have an expanded octet. Notice here phosphorus has 10 electrons on it. So if you have more than 8 electrons, those have to spill into empty d orbitals, and there is such a thing as a 3d orbital, and this expands the octet for phosphorus. Even though we can draw that Lewis structure for only 8, but if we can draw it for 8 electrons, the thing that happens with it is, notice what we get for the formal charge. It's better to put a double bond between the phosphorus and one of those oxygens. Notice how we get the negative charges on those oxygens. We can lower the formal charges to zeros. So if we can do this for the octet, this eliminates the charge on the phosphorus, which is good. The lesson is, when the central atom's on the 3rd row or below, its octet eliminates some formal charges. So you should go ahead and do that. So notice this structure here on the right is better because phosphorus loses a formal charge, goes to 0, and the oxygens are -1, which is good because it has the most electronegative element on the structure. We're going to stop there with the lecture. We've got a lot of problems to do with this for the homework sets. We'll bring those up and talk about those on Monday, but quite a bit of material here about Lewis diagrams. Thanks.